Hi, my name is Juan, and I'll be doing the final review session by myself for MAE30A, Statics and Intro to Dynamics. All right, so I'm gonna share a screen, and throughout the quarter, I personally made my own set of diagrams that were part of the extra credit during the quarter. So I think I'm gonna base my review session from those two. Well, I have from week 1 to 4 and from week 4 to 8, and then from 8 to 10, I'll base my notes on the lecture. So the first, so the first lecture was on particle dynamics. So I know that when we have a particle, we have a particle, right? And that particle has a set of forces. It can be either on X or Y, or it can also be in 3 dimensions. This will be 2D, and in 3 dimensions, it will be like this, right? So let's call this C, X, Y. Doesn't matter. Just as long as I keep everything on track. This will be a problem in 2D, and this will be a problem in 3D. And for a particle, I can have the forces acting on it, but for a particle, we said that when a force acts on a particle, it's in the same line of action. Line on action meaning that if you send the line of the force to the infinity, that's the line of action of the force. So when a particle has multiple forces acting on it, they cross the same line of action. So there's no moment around the particle because you can think about it as something that is so small that it cannot rotate along any given axis. So the only thing that can happen to a body that is a particle is to translate either in the X, in the Y, or in the Z axis, right? That's for 2D and 3D particles, but we can also have the case in which we have a body, right? So for a rigid body, right? Something that doesn't deform. So when a force is at on a body, we see that there's a principle called the principle of transmittability, that it means that either if, let's say this is a car, right? Either if you push the car from behind or if you pull it from the front, the force that the body is gonna feel is gonna be the same. That's the principle of transmittability. So if you have a force acting on a line of action on a rigid body, you can put the force here and you will have the same net result on the body, right? This time, what is different about rigid bodies is that for a rigid body, you can have forces acting on multiple line of actions, right? So you can have this force right here will generate, for example, a different moment with respect to the force right here, right? And this is now rigid body 2D and 3D equilibrium. Sorry, I forgot to mention that for particles, we can do two set of equation, two or three set of equations, depending on the dimension of the problem. So Fx equals to 0, Fy equals to 0, and Fc equal to 0. These are the conditions for a static equilibrium, which means that the sum of the forces acting on a particle or a rigid body is going to, for a static equilibrium, is going to end up being 0, right? Because the particle is at rest. Rest meaning that it's either not moving or that the motion that it had is not being interrupted by anything else, right? So it can be at rest, but it can be moving at this natural velocity, right? But since the sum of the forces is on each side of the particle or rigid body cancel each other, the particle will just move with the same velocity it had before. So that's what it means. Going back to my rigid body, for a rigid body, we can have two types of problems. Well, 2D and 3D forces. For 2D, oh, I just realized I'm in the wrong page. My bad. Yeah. This one. So you have this, right? So for 2D, up here I'm back again. My bad. So I think I was talking about 2D rigid bodies. So let's just do this real quick. So we have a rigid body. And for a rigid body in a 2D dimensional problem, we have the y and the x-axis. For the z and the s-axis, it doesn't really matter. We have that the set of equations that we can write for a 2D rigid body will be the sum of the forces on the x direction is equal to 0. The sum of the forces on the y direction is equal to 0. And the sum of the moment around a given point on the body is also equal to 0. What does the moment around a point in a 2D rigid body problem means? If you do the right-hand rule, you will see that you take the direction of the force and you curve it to the direction of the vector that contains the point and the line of action of the force in a 90-degree angle. And wherever your thumb is pointing, that will be the moment around that axis. So in a 2D problem, you can only have two moments, one moment, that it will be the moment around the z-axis, right? So you could say that the moment is either clockwise or counterclockwise, and it will be rotating around the z-axis. Different though for 3D rigid body. Also, just to mention, on a 2D rigid body problem, you can have up to 3 equations and 3 unknowns, no more than that, of course, because then you cannot solve it. Then for a 3D rigid body, once again, we have the axis, the xy, but then this time we know already, I just presented, right? We have the 3 equations of translation, f of x, f of y, f of z equal to 0, but then we can also have one moment around each axis, right? So you could have f of x, f of y, f of z, moment around x, moment around y, and moment around z equal to 0, equal to 0, equal to 0, equal to 0 in a static equilibrium problem, of course, right? So you can also have a moment around either a point or a given axis. So let's say you have a line, and the question just asks you like, hey, I have this line and then I have another force, right? What will be the moment around that line, around that axis, right? So in this case, what we gotta do, well, there's two ones to prove it, but the moment around that axis is proven to be the unit vector of the axis. Let's call this point A, point B, A, B, dotted with the cross product of a vector that contains one point of the force to any other point of the line, right? It could be this way, this way, this way. As long as it contains one point of both, the vector works. So you have R, the position vector, the cross product with the force, right? If the force is directed along parallel along the y x z axis, you just leave it like that. You leave it on the a, j, k coordinates, right? And then you compute the cross product, right? But if the force is not directed parallel to any of these axes, then I have to compute the normalization of the force with respect to the axis it is acting on, meaning that the force F can be represented as a unit vector. We saw in the third week of class, if I'm not wrong. It could be represented as lambda. Let's call a point from C to D. But this could be represented as the magnitude of the force times lambda CD, right? And lambda CD is a unit vector. And a unit vector is a vector normalized by its magnitude, right? And when you try to take the magnitude of that unit vector, the magnitude is going to be equal to 1. We saw it on class. So if the position vector is RCD, you can normalize it with the magnitude of RCD. And then you have the expression that F is equal to the magnitude, the vector F, that is the force, equal to the magnitude of F times RCD over RCD. All this to prove that this term, the force term, when it's acting along an axis that is not parallel to any of the X, Y, Z axis, it has to be normalized, just like this. So I think that will be first, second, and third week of classes. Let's go to that's moment as well. I presented moment. Oh, well, I think I didn't clarify. I think I did, but I just want to mention it again. For a 2D problem, a moment, this also moment is just about rigid bodies. Particles don't have moments. Why? Because they cannot rotate along an axis on themselves, right? I just proved that before. But then for 2D and 3D, we have rigid bodies. And in 2D, a rigid body can rotate only along the perpendicular axis to the plane. And in 3D rigid bodies, you can have around as far as 3 moments. That will mean that you could have up to 6 equations and 6 unknowns that you could solve. Or you could have more, I don't know, 8 equations and 8 unknowns, but you have to have the same number of equations and unknowns to solve for each of them, right? I presented the dot product and the cross product for moments around a point and around an axis. I took into account the unit vector. I think I would like to mention here I have statics, position vectors. Well, I don't know if I have to mention this, but yeah, if I have a vector RB, not a vector, a point RB and a point RA, then the vector RAB will be the X, Y, Z coordinates of point B minus the X, Y, Z coordinates of point A, right? So it will be RB minus RA, whatever is that value, that will be the position vector RAB, as presented here in the example, right? That will be moment of an axis, force couple. Okay, so lecture 7, force couples. I don't think I have notes about this, but I do remember the topic. So as I just proved for a rigid body, let's say we have a rigid body, right? Then I'll rather use the example of a bike. Let's assume this is a bike, right? So we have force F1 and we have force F2. They both are acting at a distance D, let's say at a distance D from each other, but they both are acting on the rigid body. So that means what? That let's call this X, Y. That means that the translational force that also they are of the same magnitude in opposite sense meaning the direction of the force. They both are acting on the rigid body, one to the left and one to the right. Even though there is a distance between them, we have that the principal transmittability, which again states that you could like the translational force that that the body is going to receive or feel, it can be directed along any position of the rigid body. It will still be the same on the translational aspect, but then on the moment, regarding the moment, the position of the force will matter, right? Because I don't think I wrote the equation, but moment, okay, I should write that. Moment is equal to a force times a distance for 2D, and this distance in 2D is perpendicular. But moment in a 3D aspect will be the position vector, RAB, and the cross product of the force, right? That's the definition of moment. That's the equation. This is around a point, of course. So it's around a point. Also, most of the problems or in the homework, in lecture, we define a positive moment to be counterclockwise direction. That's to note. Regarding force coupled systems, a force couple is composed by two different, oh my God. A force coupled system is composed of two different names, right? So a force is one and a couple. A couple is what I just wrote, or draw. F1 and F2 have the same sense, have opposite sense and the same magnitude. That means what? That the net effect of the translational force is gonna cancel on the rigid body. But if you see it, the moment they are both inducing a moment on the same direction, that this in this case would be counterclockwise on the body, right? And that moment is expressed as moment is equal to F1 plus F2 times the distance between the two forces, right? Also, yeah, that's right. That's for 2D, of course. Then for 3D, I do not remember the equation, but I'm gonna look it up right now because this is a practice. Yeah, of course. So for 3D is the same, right? This is 2D, this is 3D, and for 2D is R cross F, where F is the force vector at the tip of R. So R is this distance in this case. R is this distance, and F of is the force, right? So that's our couple system. But then a force couple is another statement that says that, let's say I have 5 forces acting on a rigid body. I could replace that set of 5 forces with one set of one couple and one force. Example. Do I have to do examples? I don't really know. There was one question in the quiz that was a little bit tricky, I guess. But we have, I don't know, like 6 forces here. Points A, points B, point C, and points D, right? One force and one moment on the rigid body, and this was attached to the wall, let's say, right? So the force couple system of statement says that if you have multiple forces on a rigid body, you could easily replace that force with one couple force, that is the one I just draw at the top, and one force, right? How is that valid? Well, if you think about it, principal transmittability says that you can shift the force along any direction. It will have the same effect, but it will change the momentum, the moment on the rigid body, right? So if you add up, let me write it down. If you add up the contributions of all the forces along an axis, right? Let's say you have F1 plus F2 F1 plus F2 plus F3, you could have a total force that is exactly F1 plus F2 plus F3, right? But then that force is going to induce a moment on the rigid body with respect to a point. So I will also have to take into account that there is already a moment on the body, right? So I have to do the moment, the sum of the forces. No, 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 no. I will have to do the sum of the moments, right? And then there's gonna be each force is gonna have like a contribution to the moment, and I can add a moment m. That moment m indicating that that's the moment of the couple. I don't have to write the couples on the diagram, for example, because they cancel each other. The only thing that doesn't cancel is the moment that they are generating to the rigid body, right? So in conclusion, for lecture 7, force coupled systems, I can have I can replace the entire set of forces on a rigid body with one force and one couple. And the way you find out the distance in which the force have to act and the moment that you need to have in order to replace all those sets of forces can be found by setting up the equation of equilibrium, which is not really an equilibrium, it's just the equation of the sum of the forces and the equation of the sum of the moments, right? And finding that moment and that force that will give you an equivalent system. Equivalent meaning that is in both directions, right? Both represent the same. That'll be that for lecture 7. Yeah, I went ahead a little bit and I was talking about equivalent forces. That's the next lecture, of course. I do also I skip important things that I would have like that I would have liked no. I would have liked to set these things before at the beginning, but there are topics that I skip that are cosine. No. Yeah, cosine direction angles. Cosine direction angles. Cylindrical angles? No, cylindrical. What's the name? I forgot. Yeah, my bad. So it's cosine direction angles and cylindrical coordinates. Both are really useful at the time of trying to solving problems because they give you like if you're given a little bit of the dimensions and then you're given an angle, you can use the sine or cosine theorem to find, I don't know, maybe the diagonal using I don't know, sine of theta equals to r over d. You could maybe solve for d if you're given the angle. And just a quick thing is that the unit vector of the cosines square of each angle is equal to 1. So I can use this identity as well to solve for an unknown angle. So if I can have theta x and theta y, I know the lambda, that will be the magnitude of that vector, of the cosine direction angles vector, will be 1, and I could solve for theta c, right? That is what we did in the first take-home portion of the first quiz. I solved for theta c with this identity. That is really useful, and just a reminder for myself is that theta x, theta y, and theta c is the angle that a force or a vector makes with that axis, right? So just quick reminder to help myself is if this is x and this is the force F, this will be the angle theta x, right? And for cylindrical coordinates, the angles formed this way. I might be misleading it right now, but let's call this theta. Now let's call this psi. Then this angle is theta, right? And the radius can be expressed as rho sine theta sine phi. If I'm not wrong, I'll check it up right now. Yeah, so I was confusing myself a little bit, but for cylindrical coordinates, C is just C, and then for spherical coordinates, the part that will be C is rho cosine phi, right? The angle phi. And yeah, I wanted to mention that before going to the lecture 9. Lecture 9 is pretty much based on, let me go to lecture. Oh, I should have done this way before. Nice. Yeah, so lecture 9 is based on reaction forces. So I remember pretty well on this lecture we saw rollers. So rollers is a type of support that lets you slide on the horizontal axis, but it presents a normal force on this axis, right? So when you draw the FBD diagram, the free body diagram, I could say like, hey, like the the rollers are supporting on a structure, right? But they only have a Y component. Let's say this is a Y component, and the support is free to slide on the X direction, right? So there's not a force there. The only restriction force is in the C direction, because if you try to push the structure down, the roller won't let you, right? But if you try to roll it, it will let you. So that's one type of support. We saw rockers, surface support. Then this type of surface, they have both the two components, X and Y. Try to push it, try to like lift it, it won't let you, right? Well, technically it is presenting a force on the down direction of the down to Y. But if you do it up to the Y direction, if you have enough strength, you could lift it up. But it's not presenting a force in that direction. So technically the force will look like this. There's a force. There's a restriction force in this direction, and no, it's there's a restriction force in this direction, and there's a restriction force in, if I try to pull, take it down, it won't let me, right? It's in this direction. That's for a surface support. Oop. We have a P, so I'm gonna just go through the ones I remember to be the most important for me. So hinges, a hinge is the design we see right here. They have X and Y support. Also, I'm calling this on the 2D, but it can also apply to the 3D. It just depends on the setup of the problem. Hinges, hinges have both the Y and X support, right? Because if I have a scissor and I try to pull it in any direction, it won't let me, right? But if I try to rotate it along the perpendicular axis, the hinge lets the two parts of the scissor rotate, right? So there's an X and Y restriction, but there's no moment restriction perpendicular to that X and Y, right? Color slider, well, I remember this, kind of complicated to be honest. So since it's complicated, let's just think about it. So yeah, so a collar is composed by two, right? So there is a hinge that is attached to that tube, and that tube is free to slide, right? It's free to slide on a diagonal, but then the hinge allows for moment, but it doesn't allow for X and Y movement, right? So it's like a combination of two type of supports, and we saw in class when Brian gave us a universal joint that the joint was able to rotate around two axes, since it was composed by two different hinges and one like support. It's not here anymore. Yeah, well, it was here. Um, yeah, the universal joint, right? This joint allow us to rotate around two different axes, but not around the third one. and it was connected by two hinges. So that's like, I guess it's gonna be an important thing on the final, and I should understand it pretty well. But yeah, going back to this 2D, we have hinges, color sliders, fixed supports. Of course, a fixed supports won't let you move in any direction. And I will say, yeah, those are the most important steps I have to take into account. This is called supports, and these supports have reaction forces that are pretty important to take into account the time of analyzing a problem and doing the FB diagram. Also remembering that there's some supports that allow for translational motion, but they don't allow for moment, for example. And there's other supports that are exactly the opposite. So I think it's very important for me to identify them. Going to lecture 10. So lecture 10, that is around week 6, oh, am I? Yes, okay. So lecture 10, that is around week 6, is also about reactions, but then this is in 3D, right? So I have to take into account X, Y, and Z axis. Pretty important. Um, as I was talking about before, the universal joint. For example, our shoulder is free to rotate in any axis, right? But when you try to pull it, well, good luck. It's not going anywhere, right? So that's called a ball or a socket support. Uh, yeah. So from this lecture, I would like to emphasize, for example, this problem, identify them. So at the beginning, it was a little bit tricky, but I think that as the weeks go by and I do more problems, I was kind of able to identify what were the reaction forces for a given system. So let's say at B, this is a 3D rigid body problem, right? Rigid body because, well, it's an entire body, I think it's a pipe. At B, for in the y-axis, it's free to slide, right? But then you try to pull it on the X or in the Z-axis direction, and you can't. So you could technically say, you can say that there are two reaction forces right there, one at X and one at C. Where do I want to put direction? It doesn't really matter as long as I keep it consistent throughout the problem, right? And at C, well, I haven't read the problem, but it looks like C is also another type of support as B, right? So it seems that along the x-axis is free to slide, but along the other axis is not. And somebody will think, I used to think, oh well, it makes no sense. Like if I try to move B along the y-axis, it's not gonna move because it has a restriction on A. But then with time, I understand that I have to analyze the components by themselves. So I have to see A, I have to see B, and I have to see C, and see the reaction forces. Yes, the system will interact in a specific way, but at the time of identifying the reaction forces, I have to do it for each component. So that's pretty important. So at C is the same case at B, but in this case, it's free to slide on the X. Same case for A, but this case is free to slide on C. And I think I haven't read the problem, but for this picture, I think that there's a circular rod and there is a circle of bearing. So you cannot, it's free to rotate like that support right there where the F1 force is acting is free to have a moment around the C axis. There's no restriction right there, but it's also it's free to slide on the C axis, but you cannot move it along any other direction, and you can also not rotate it along any other direction. Another thing that I do remember a lot from class is, let's say I have a square or rectangular rod, and that rod is inside another support that is also rectangular. Professor, she said it's impossible for it to for a rectangle to rotate along another rectangle, right? So, so if that is a rectangle and this is a rectangle, uh, assuming they are almost the same size, the rectangular rod is not gonna be able to rotate along that one. So there will be a moment restriction right there that it doesn't seem intuitive at the beginning, but then you kind of see it, but it's easy to ignore it, right? It does can move along that axis though, so that's important too. But I think that will be it for lecture 10. Now let's go to lecture 11. Yeah, so lecture 11 is about trusses. I think this was, I guess, from the class at the beginning, it was one of the most not complicated but confusing topics in the class, right? What is a truss? A truss is pretty much a multi-dimensional structure that is composed by multiple members, what we call members, that are those little rods right there that compose the structure. Yeah, so for a truss, we said a truss can be considered a rigid body. And we said that for a truss, it can be, as we saw in class, if you apply an external force to a truss, each each truss member is going to receive or feel a different type of force. Well, it's actually only two. So it's either gonna feel compressed, as we see in the picture, or it's gonna be in tension, right? Although we cannot know. It depends on the problem, right? Also, each truss, for example, in this example right here, this is this this one right here has like four members, three members, sorry. And at the joint, since that truss is at equilibrium, I can also induce or think or conclude that that joint is at equilibrium right there. So if there's a force on the left axis, up, so right here, if there's a force here, a force here, and a force here, if this thing is the part of a truss member, that joint we call a joint because it joins all the members right there. It should be at equilibrium on the X and Y direction, right? And I think we only did with two-dimensional trusses, if I'm not wrong. I think so. I do not remember dealing with three-dimensional trusses. But important parts of a truss as well is that we can have zero force members. That means that they are not contributing to the sum of forces on the truss, but they're still really important because they add equilibrium. And the condition for a zero force member is that you have to have, actually, I don't remember. I think I do remember. So these are three members, right? And these are two collinear. This is one, this is two. These are two collinear members, right? As I can just from looking at it, I can see that the two members, they are parallel to each other, right? So they only act on their forces, if they have forces, only act on the X direction, right? And also I know that the joint has to be an equilibrium. So just by conclusion, and since this third member is perpendicular to them and they don't have a Y component, then that's a zero force member because there's not a force right there, but it adds equilibrium to the entire system. So that's, at the time of solving problems, that's an important tip to know. But yeah, there's two conditions. Let's look at it. Two non-collinear members are connected at a joint. No applied forces or reactions present at that joint. Yeah, right. Both members are zero force members. Oh, that's really interesting. I guess that's true as well. And the condition two is three members connected to a joint, two of the members are collinear. That's the condition I just explained. But this, let me review this condition again. Two non-collinear members are connected at a joint. So I guess for condition one, this is these are two members and they are not collinear, right? One and two. No apply force or support reaction present at that joint. Well, yeah, so this pretty much is saying that if this is a joint and there is not an external force acting on that joint, and there is no reaction forces that the joint is applying, then as a consequence of by extension of that argument, these two members are non-zero. Sorry, zero force members, right? Because there's no force at all. So that's one thing that I guess I forgot. Yeah. Important thing of this lecture as well is that we got introduced to the knife of MAE30A. The knife, pretty much what it does, let's say for this example right here, as I can see, as everybody can see, truss has multiple parts and it will be just really difficult to keep adding up all the sum of the forces at each joint and each external force only to get to a specific point I want to analyze, right? So another method that we got taught is that we can use a knife. Meaning what? Meaning that you can cut the truss at a specific section and you can analyze either the left or the right of that cut, right? So right there when where you make the cut, for example, in this, let's say in this example, professor cut right there between H and G, right? And she right now is analyzing the right side. So those forces that are acting to the left, FGH, FDH, those forces are there, so they have to be taken into account. But the truss has been cut right there. So at the moment of analyzing the sum of the forces on the X, Y direction and the sum of the moments, we can assume only to analyze the right side and solve for an unknown that we have in the right side. And we can do the same for the left side. How do we decide that? It depends. It depends on what we want to analyze. So that's the thing. So I do remember a lot that for this type of trusses example, we usually have a support on one side and a roller in another side. And then at the beginning you have to take into account the entire rigid body, but then to solve for another, I don't know, the force at a joint or the force at a specific member, you have to use the knife, cut it. So for the unknowns, and then use the other side to solve for the other unknowns. I will say that's pretty much about it. Also, I didn't mention it, but just by definition, if you have a 3D rigid body and you're trying to take the moment, then I should write this instead of talking. If you have a 3D rigid body and you take the moment around a point A, let's say in this picture. Let's say you want to take the moment around point C, right? Right there's an external force at point C. So by definition, that force is acting on the particle C, meaning that that particle C is not gonna receive or yeah, it's not gonna receive a moment due to force C right there, right? So when setting up the equation, all those forces that are in the same line of action of the point, they will not count. It's not that they will not count. They will not generate a moment around that point. So that's pretty important at the time of using truss and brain and machine analysis is to take the moment around those points that will cancel the most unknowns as I can, right? As I think we did it in this example. Yeah, the moment around H, on H we had what? FGH, FDH. So professor was able to cancel all those forces just because they were acting along the line of action that of point H, right? And we were able to solve for FDC in this example. But that's something that is, it can be difficult to analyze and it can be tricky at the time of doing exams because we could get a lot of equations and not that many unknowns, even though they are there, but we have not seen the way to find them. So that's really important at the time of doing these type of problems. So let me go to lecture 12. Recording? Yes. Okay, so lecture 12 is titled Frames and Machines. So the good thing about frames and machines is that you can get a like as well as the pull legs in the gym for example, you can gain a mechanical advantage by inducing a force on a certain part of the rigid body, and you could get a much higher force in another part of the rigid body, right? Just by pure mechanical advantage. Uh, Important to understand is that is the difference between trusses, frames, and machines. Trusses, yeah, okay, I forgot. I haven't, no, we haven't mentioned it yet. But yeah, trusses are composed of all two force members and are stationary, so trusses don't move at all. Rigid static bodies. Then frames is a mix of two force members and other type of members. Known as what is a two force member? It's a member that is receiving a force. Is in the last lecture as well, I guess. Yeah. Oh yeah, I forgot to mention it. A two-force member is a member that is either at compression or at tension, right? It's one of two. So when let's say you cut a truss right there in the middle of that two-force member, in the right free, oh, let's just draw it. Let's say this is the two-force member, and you cut it right here, and this is a tension. I could either analyze it as it was a tension or as if it was a compression. But when analyzing this part, I have to take into account that the free body diagram for that force is going to the right. And when analyzing this part, I have to take into account that the free body diagram for that left plane of the two force member, this is a cut, is going in that direction. That is really important because if I don't keep track of that sense of the force, it will mess up my calculations just because of a negative sign. That is actually what happened in one of my quizzes. So I guess it's really important. It is really important. But back to friends and machines. Uh, this is only examples. So frames and machines. Yeah, so a frame is a mix of two force members and other members. Here's an example for myself. This is a frame. Well, it technically moves, so I don't know anything. Oh no, okay. It's generally stationary, so yeah. I don't remember the name of this gripping. I don't remember the name of this in English, but this could be categorized as a frame, right? And then you have machines that are composed of multiple two-force members, multiple other parts, and they will move, right? They will generally move. That is pretty much any mechanical device that we see, cars, airplanes, motors. Well, motors, the pistons of the motors are moving. Those type of machinery, right? So for this type of problems in which we have a frame or a machine, we also use the method of the knife of MAE30A. So these things are rigid bodies, of course, right? Because just they are composed of multiple things and they're connected together. If it is an so oh also I forgot to mention, but when you analyze this type of rigid bodies, inside the rigid body we set it to be at equilibrium, right? I do remember the example in the book and in the class that if we have a car, the norm and this is a guy sitting right here, the normal force that the seat is exerting on the driver is equal to the weight of the driver, but all that is inside the car. So it's irrelevant to any analysis that I want to do because the only things that I want to analyze on the car or that will imply something of important that is important to analyze will be external forces, right? Or if the problem is asking me to find an internal force, well then I could neglect all other forces that are not exactly connected to the internal force I want to analyze. So back to frames, we have two examples. I think it's always worth it seeing the one of this one. I guess it was really tricky one, but this one could be considered a machine. Important thing right here is this is about I don't know the name. It's a truck. I don't remember the name. It just has a bucket that picks rock, right? Those rocks have a weight, are pretty heavy, so their weight will generate a moment around point A, and around any point, right? You have to be strong. The parts of the machine has to be strong enough to support all that weight, so that it doesn't tilt to the other end, right? It doesn't rotate. But I think this problem was asking for the force in specific members, and it just to stand out, not to be here all the time. This type of problem has a lot of dimensions and it has a lot of components, so it was really important to divide it by parts. That's what we usually do for this type of problems. So one part was the bucket, and if I see right here in the bucket, I could say that I cut it between AB and between DC and between DE, right? Yeah. So A and D are supports, right? And the forces that they were exerting to the other members were internal. But since I cut it right there, then the forces are exposed and I will have to analyze them. And in this case, I think we were being asked for FAB, so we were able to find FAB for that problem just by cutting right there and considering the external forces, right? Taking the moment around D, if I'm not wrong. Yeah. And finding the force FAB. For the next part, we also it's important to there are three sections of the machine that are two force members, right? CV, what DC, FH, and AB. DC, FH, and AB. I do not know how to explain how to identify them. I oh, I guess it's a tricky one because I, I relate a two force member to a truss, all right? And when you see a truss, you see a lot of triangles. And in this case, in the machine, what you see as a triangle, like what you specifically see that relates the most to a truss are DC and FH and AB, right? For them to be two force members. Two force members meaning that they're either a tension or compression. But I guess I don't know how to identify them. I should know. I'll be back and give an explanation for this. Yes, so coming back, I'm doing a little research and just reviewing the notes. The key thing to identify a two force member is identifying that first it has to have, it doesn't have to have, but like to be connected by 2 points, right? So by two pins in both sides. Then there should be only one force applied to them on each side so that we can know that it's either at tension or it is at compression. Besides that, there shouldn't be any other forces or couple or moments in that two force member. And just as a reminder, it is acting along the direction of that member. So if it's diagonal, well, the force is acting diagonal as well. But that will be for two force member and for this example. Friction notes. I guess this was one of the most simple topic of the class. Friction, on the microscopic scale is pretty much generated by a roughness of a surface because I don't think there's a single surface in this world that it has zero roughness. So in the microscopic view, I can think about it as if there were two surfaces gripping each other, and they will be governed by F equals ma, right? So that's Newton's first law. Yes, F equal ma, if I'm not wrong. The first one. Yeah, third one is the reaction has an equal another an opposite reaction. The second one is the conservation of momentum. I think so. You'll be right. I'm not gonna check it. But yes, so recording, yes. So professor said in class, friction sometimes is fun. Why is sometimes fun? Because we have two types of frictions, right? So if this is being the force applied to a surface, we have a peak and then we have like an exponential decline that it goes tangent to a given line, to a given horizontal line. This part of the friction curve is defined as mu s n, right? What is n? N is the normal force. What is a normal force? Normal force is the force that the surface, normal force is the force that the surface is giving or acting on the object that is on the surface. Yeah, that's what it means. That's what it is. That's the normal force. And the mu s is the coefficient of a static friction, and it's different for any other surface. So it's usually a low number, 0.1, 0.2, 0.007, stuff like that. But then that is when friction sometimes is fun. Because as we see, if I imagine like this is a surface and I have a block and I'm pushing a block. At the beginning, there is more resistance, right? Just from real life examples. You push and you keep pushing and you apply more force, and there will be an impending motion, right? And not an impending motion, but an impending force that is the friction force that is with the static friction coefficient right there. But when the moment, nevertheless, the moment in which the force that you apply is greater than this force right here, that is the maximum static friction that the surface will like oppose. The moment you do a force greater than that, then the friction force is gonna shift, and it's going to shift to a kinetic, not a kinetic. Yeah, to a kinetic friction, right? It's right there. That case, this part right here is mu k times n. Mu k being the coefficient of kinetic friction that is gonna be different. And just as an example from real life, you're trying to push a car. well, I don't know how many people push a car. Push a car. You try to push a car at the beginning, it's really hard, right? It requires a lot of force, but once it starts rolling, it gets way easier. Why? Two things. First, it gets inertia, right? So that helps you push it. You feel less, or that you're applying less force, but you also have the friction is also less because now that is rolling, the coefficient is less. So whenever it's moving, the friction is less, but it is still there. So I do remember in the first, not even in the first quiz, in the pre-quiz for this class, there was an example of a box, and it was asking what will happen to the friction force, if and even though like the mathematically you don't see it, not mathematically, so the problem says you have a box and you're applying a force. If you keep applying, if you apply more force, what will happen to the friction force? And I personally respond that it was going to increase. I was wrong. Now I know that it won't change, right? Because it has a cap, it has a maximum, and the box was not moving. So if it is not moving and I apply more force, that is because the friction force was acting this way and the force that I was doing was acting that way, right? So it's not gonna contribute anything to more friction force, right? That was the mistake I make on that exam. But I think that will be it for friction. Yes, just as a recap, there's a part of the friction. The linear portion of the friction will prevent motion, and it's proportional to the force I apply, to the force that is being applied. And then there's a part that will have motion, but the friction is still there. It's just less, and it has another coefficient, right? That is the coefficient of kinetic friction. Just from doing some free body diagram analysis, there's an angle of friction as well. That angle can be used to find if we are given the forces and the weight, we can find the normal force, and with those components, we can also find that the angle, and with the angle, like, we can find the coefficient of friction. So that's important to take into account. I do remember this example. Maybe it's important for me to. I should go faster. Well, yeah, in these examples, since it's two rigid bodies, there's multiple cases. There's actually four cases. First case is that the top slides, bottom stays still. That it will be like the most common case. Somebody will think, especially if you're pushing from the box on top. Both boxes slid together. That will be the case in which the friction between the two boxes is way too big. So the friction in the bottom is smaller. So both will move first, right? And that could happen like in, say, on your own water, or the surface is just really wet and the kind of coefficient of friction is really small. That could easily happen. We see it in real life a lot of the times, but then you have the other case in which the top box could tip, or both boxes could tip as well. I think at the end we proved that both boxes will tip together. That is one of the, it's not intuitive, but it can happen, and we proved that. How do we prove it? Whichever case requires the less force is the first one that is going to happen, because you start applying zero force and then you just go incrementing, right? So whichever 90 pounds was the less force, therefore that's what's going to happen first. I go to lecture 14 and I go to lecture 20. I'll try to do it faster because it's taking a lot of time. I don't think the TA will be seeing this, but at least I get my extra credit. I'll take a couple minutes in the next one. All right, so lecture 14 is called centroid. Main takeaway from this lecture is that there's three important parameters I should know, not only their definitions, but their formulas. Center of gravity is where the resultant weight weight being m times g, is acting on the body. Also remembering that for a rigid body, so you can have a rigid body with constant density, but you could also have a rigid body without constant density, right? So the center of gravity, well, take issue, right? The center of gravity is the resultant weight of the system and it's gonna act at a position x bar, y bar, right? The center of mass is the point of the rigid body in which you could say the mass of the body is accumulated. So there's one point that describes that behavior of the rigid body. And the centroid is just the geometric center of the body. That I guess is the more intuitive. The one that is not intuitive at all is the center of mass or the center of gravity. I like to think about it, the center of gravity, as if I have a rigid body and I could just magically put my finger in in one point of the rigid body. If I put my finger right there, it will balance out, right? Why? Because for a rigid body, its mass is distributed along the rigid body, right? So the weight is acting on each point of mass, but there's a point in which all those weights group up and specifically they add on that point. It doesn't have to be necessarily on the center, it depends on the geometry. So we could have the case that the center of mass, center of gravity, and the centroid is the same point for a rigid body, but we could also have different cases in which that's not true. So quick recap, 3D rigid bodies, we have x bar, y bar, c bar, and it's defined by the integral of x dw over the integral of total weight of the dw, which is the total weight. We have first moments, moment of inertia. What does moment of inertia means? It means that the body has a tendency to rotate around a point, right? So how is that described? It's described by these equations right here, xdA equal to qy and ya is equal to the integral of yda equal to qx. And you can have these moments of inertia with respect to an arbitrary axis that you pick on the rigid body, right? So it doesn't necessarily have to be at the origin, like right here. You could just start the axis from the centroid, and you will compute a different moment of inertia. So I guess this is a main thing I should keep in my notes. Um, not only the definitions that I already know and I think I already understand, but also the formulas one is necessary to compute them. So just quick recap, each shape can have a different centroid. Well, it not can have, it will have a different centroid. So there's some centroids that you could either compute it or they are already tabulated on a table. So for triangles, for semispheres, or for parabolic areas, is governed by these equations. So if we have those parameters, I could find it that way. But if a body is composed of multiple shapes, as we saw in the quiz, not in the quiz, but in the homework, I could, as in this example, I could add up all the contributions of each shape and compute the x bar and y bar of that entire shape. That is what I'm gonna do. There's an example I would like to show right here. So for let's say this body is composed of multiple shapes, if each shape separately has a centroid. That centroid, of course, it has to be taken into account from a reference axis. So in this case, this is the origin right here. And then I'm just making sure when using this table, I have to put the centroid in reference to that reference axis. So that's really important. If not, I'm gonna get the wrong value. Then by summation and division of this of the areas, I get the points of interest, X bar and Y bar of the entire figure. That's one way, that is by multiplication and summation, but I could also do it the calculus way, that is by direct integration. So I will have to identify if I have a curve and another curve, they overlap and they describe a shape, like in this case, I will have to find the X bar, Y bar by integration of X dA over dA and Y dA over dA for Y bar, right? So I guess this one is a little trickier, but we already saw it in calculus 1B, in my case 1B at Magnetic College. So I think it's not that difficult to identify the curves, just the points of intersection A, B, C is important to take into account. And just remembering that dA has to be described also by a reference axis. So in this case, dA is described by y1 minus y2, right? Because we take a vertical strip or we could take an horizontal strip. It doesn't really matter as long as we integrate with respect to the right variable. That's for the first moment of inertia. Let's go to lecture 15, that is distributed loads. Yes, so let me pause right here. For distributed loads is actually the case which it reflects most the reality. For example, center hall, right? The second floor, you have multiple people stepping on different areas of the building, right? So the load or their weight is acting is being distributed different along that building. It's not acting on a single point. So that's how I like to think about it. Um, but it just refers to that, like you have a load per meter area, so per meter area or per meter length. So at the time of analyzing the sum of the forces or the moment, it has to be analyzing in such a manner. And in this example, we have this beam. It has a distributed load. Luckily, we have the at point A and at point B. They gave us 15 kilonewtons and 10 kilonewtons. Then I can use the geometry of that information to get the centroid. Right, yeah. To get I can use the geometry. So I can identify a triangle right here, a rectangle right here, and another triangle right here. And use that geometry and use what I just explained in the lecture before to find X bar and Y bar. Taking into account though that this is load per meter, so it's force per meter, it will be is that pressure? No, that's not pressure. Um, it could be seen as pressure, not really, because pressure is per meter square. Linear pressure, I could say instead. So it's a linear pressure on each length of the beam. But just once again, as I just explained in the lecture before, you can use the method of multiplication and summation to find X bar and Y bar, and this could be used to replace the load at a given point. In this case, the resultant load will be 75 kilonewtons, and X bar is 1.2 meters. And Y bar, there's no Y bar. Mm, measured from point A. Well, yeah, there's no need for Y bar because it's just Y bar will be along the. Let me think. Yeah, right. So there's only an X bar in this case because the question is specifically asking for for the position in the x-axis in which you can have a resultant force equivalent to distributed load, right? And there's no y bar because the beam is just horizontal. So there's no y component of it. That will be it for lecture 15. Lecture 16 is moment of inertia, so it's the double integral of the moment. Um, I do remember a lot from professor in class that he did the example of applying a force at the tip of a pin that has a rectangular shape or that has a T shape, right? And it would be way harder to induce a moment around a lesser area, right? So it just doesn't bend as much as if you have an entire area that you can apply a force around it, right? So that's why we have this type of shapes because it's just way harder to break that because it's just like the tibia bone. From the side, you could easily bend it, but from the front, it's just almost impossible. Yeah. Yeah, and the moment of inertia is described by these two equations. I of x is the integral of y squared dA, and I of y is x squared dA. It's fairly similar to the lecture to 2 lectures ago, but this time is just x squared. We still use the same method, the vertical and the horizontal strip to analyze, but just with an x squared or y squared right now. So in terms of math, it's almost the same. Maybe just a little bit more of math. But yeah, I would say that's the same. The only tricky question about this type of problems is it's just identifying the A and identifying, I will say just the A and the interceptions, of course, if we have the problem in such manner. Once again, we have tabulated shapes in which we can have the moment of inertia. Also, tricky question about this though, too, is that for these shapes, you have Ix bar and Ix bar prime and by I bar Y prime. Why? Well, that moment of inertia, as I expressed before, could be different for a reference frame or for a reference axis. So in this case, in this figure right here, I see Y prime and X prime. Uh, and the moment of inertia, Ix and Iy, will be at a different position, right? But then for y and x, that is located at the origin, we will have a different value of moments of inertia. So computing the integral, this comes of course from the integral, right? But computing the integral from a different reference frame is gonna give you a different algebraic equation. So that's important to remember. And that could be for any other shape. So that's really important. Parallel axis theorem, I saw it in physics 4A once again. Yeah, so just to read, relates the moment of inertia MOI of an area about an axis passing through the area's centroid to the moment of inertia of the area about a corresponding parallel axis. So what does it mean? It just means that if it just means that the moment of inertia of the centroid contributes to another moment of inertia from a different reference frame. So I explained I I y bar prime will have to be in the equation for another different area. They will have to add to the moment of inertia for another different area. So right there we have the two expressions and you can see how they both contribute to the moment around that from that area represented right there, right? Dy squared dx squared. Yeah, once again, we have an example right here. I'm not gonna go through it, but we again just quick use the method of summations, identify the different moments of inertia for each shape, right? And then just add the contributions for ix prime and y bar prime. I think y bar prime, it was not needed because the figure is symmetrical around the y across the y-axis, but around the across the x-axis it isn't, right? So and also it's computing from a different origin, right? From the centroid of the figure that is shifted from the origin. But that will be lecture 16. Lecture 17, I think, okay, lecture 17 introduces us to dynamics. I think it's a more exciting topic in my opinion, to be honest. But dynamics, we have kinematics and we have kinetics, right? What does kinematics means? It's the study of the geometry of the body or the particle. I also like to see it as there's no forces. There is forces, but never mind. It's just the study of the geometry, in which we mainly neglect the forces, except for gravity. So we have the rectilinear for the parabolic, rectilinear parabolic type of movement. I think that's the name. Just example from when you're shooting something from, it's not here, I guess, but oh, right here. Projectile motion, that's the name. This would be a type of kinematic problem, and these are the kinematic equations. We saw it in physics for it, so I think I'm pretty comfortable using these equations. But then we also have kinetics that this is the first time I think I'm seeing this type of kinetics. I saw it in the past, but not like I see it right now. Kinetics is also concerned with the forces causing motion, right? So we have a forces and we have that the sum of the forces equal to the mass times an acceleration. And we're interested in that acceleration, right? So that would be kinetics. We have particle kinetics. So for for a motion, you can have different type of motions. You can have rectilinear, meaning it moves in a line. And you can have curvilinear, right? Meaning it moves on a curve. And for curvilinear as well, you could either have a fixed radius, a moving radius, and a moving angle and radius. So I guess I'll see it in the future lectures, in the next 2 3 lectures. But yeah, in class we went through a lot of stuff. Well, not much, but we we didn't derive the equations, but we were presented to the intuition of the derivation of the equations. And we know that the velocity is just the change on x over the change of time. Acceleration is just the change of velocity over time, and so on. So you could prove this differential equation. It's a single ordinary differential equation, right? So you integrate that and you can have, and you get these equations that describe a kinematic motion. Okay, this was a good example in class to, I guess, to get the intuition of a kinematic motion. Just I guess the main takeaway from this problem is just taking into account that the velocity there's different values of velocity for the car for different times. So there's a t0, there's a t less than 0, and there's a t greater than 0.75. You have a different type of motion. Why? Well, just because of right now, just because of the problem after t 0.75, it starts decelerating, right? So it's not a constant velocity, it, it's at a constant deceleration, so we take that into account. But yeah, from the dimension and the gain information, This problem was fairly easier, just with a little bit of intuition, setting up the right motion of the cars. It was really important. Relative motion is also a topic that I saw in calculus. It pretty much it just changes the reference frame of anything, right? So right now I could say that I'm moving at a speed of 0 meters per second, so I'm at rest. But then if there's an spectator, let's say in the sun, and he's looking at me, then to him I will be moving at what? 220 kilometers per hour, right? Because the Earth is rotating around the sun and it has around that velocity, if I'm not wrong. But actually, I just guessed that. Let me double check. Yeah, so I underestimated the velocity. So the velocity will be around 30 kilometers per second, right? So if there's a spectator in the sun and his reference frame is that he is at rest, then my velocity with respect to him will be almost 30 kilometers per second because the Earth is moving at that velocity and not the Earth, right? So the reference frame can change and it's dependent on the spectator. So that's what the equations say right here. The velocity of B with respect to A is just the velocity of B minus the velocity of A. That's pretty much what it means. Okay, here, I like this problem. I actually think it's gonna be in the exam. Though I don't know how, I just think so. Because it's like a good question to have in an exam. I think this is kinetics. I don't know, this is not kinetics. This is kinematics. But it's just saying that the length of the cable is not gonna change, right? So for every movement on a direction, you'll either have that the length increase by that same amount on the other side, or it decreased by that same amount on the other side. So anywhere between anywhere here, for example, right here, XA and YB are changing, right? But there's parts of the cable that will not change. It will remain fixed. And the total length of the cable is also fixed, right? That's a constant. So you could make an expression for the length of the cable to be equal to XA plus 3YB plus 2L, right? 3YB because there's three cables in between YB. So if you make that expression, you set that as a constant, you take the derivative with respect to time, you get what? The velocity, right? You just out of distance, you just got a velocity by taking the derivative and solving for the unknown you want, right? So I think that's really important to stand out. Then going to lecture 18, for bilinear motion, there is the one I was talking about. This case, we have is motion along a curve. And this type of motion is different from rectilinear motions because now the acceleration component is different, right? So you have a tangential acceleration and you have a normal acceleration. Tangent, tangential, well, tangential just by definition is a tangent line to a curve is a line that only touches the curve at one point, right? So anything tangential to anything else only touches the line at one point. So tangential acceleration and velocity for a curve. Let me write it right here. If this is a curve and it has a fixed radius, this will be for it to be a fixed radius, it will have to be a circle, of course. Yes. And it will have this is tangential, right? So if I'm here and going on the curve, I will have different tangential components all along the curve, right? And then my acceleration, my normal acceleration acts towards the center of the curve. We derived in class that the total acceleration for a curvilinear motion is described by AN plus AT. AN, again, normal acceleration, AT, tangential acceleration. AN, we derived that it was the velocity squared over the radius, and AT is just dv dt, where dv is also the dv is tangential to the curve, right? It's a vector tangential to the curve. That's what it means. Let's see what else do we have. We got introduced to average and instantaneous. I guess we already know it since it's one of the prerequisites for this class. But yeah, main takeaway from this problem is this set of equations, right? Could be linear motion in rectangular coordinates, but we could also have a different type of coordinates. Oh well, actually, yeah. So you could have curvilinear motion in rectangular coordinates. That is right here. Yeah, and I already explained the tangential component. We have this example we solved in class, but then the other one is normal and tangent coordinate system. Uh, the difference is that it also expresses a curved motion, but this time it has different. It's a different set of coordinates, right? So as we saw in linear algebra, I can change the basis of any coordinate at any time, just for the ease of computation. So you have this time we have a component u of t and u of n, right? That is a different set of components. One is tangential, one is normal to any point of the curve. That's pretty much what it means. And that's what I was explaining for the acceleration. That will be the expression that we have right here. But yeah, that will be it for lecture 18. For lecture 19 is an intro to kinetics. Let me pause real. For lecture 19 is an intro to kinetics. Um, just again as a reminder, kinetics is just the study of the movement relevant to the forces. So the sum of the forces is equal to the mass times an acceleration, right? So this is not a static equilibrium. Like the object has an acceleration, we just have to find what it is based on the type of forces we have studied, that in this case are physical forces. And we can also have cylindrical components. So this time the coordinates are, instead of ut or un for normal and tangential, we have a radius and we have an angle, right? So we have a cylindrical. See, those will be cylindrical coordinates, right? So in the class, we derive a set of equations that describe the velocity and deceleration for cylindrical polar coordinates. Polar meaning using the radius and the angle theta. Cylindrical meaning the same in 2D, right? And in 3D, just adding another component that is the c-axis. But I guess important to remember is that the velocity is r dot ur plus r dot u theta, where r theta and no r dot and theta dot are functions of time. R is in this case, most of the cases, R is a function of theta and theta is a function of time. So that's important to take into account because now we have to apply calculus rules. So the product rule and the chain rule for this type of cases to derive this equation, which is right there. Following the same logic, we didn't derive it, but we derived the intuition for the expression for the acceleration. So for this type of problems, it's important to identify a function for the radius. And probably, I don't think we have identified in the homework a function for the angle, it probably will be given as well as is corresponding derivatives. But in the homework, we did do a derivation for the equation of the radius that is mostly a function of an angle, right? If the radius is constant, right? That's what it means. And this is the big picture. I guess this is the main takeaway from this lecture. As I explained before, the sum of the forces equal to an acceleration. I guess from kinetics, to solve problems, it's important to draw separately the free body diagram and the kinetic diagram. Why? Well, I mean, we don't have to, but just for the ease of understanding, it's easier if you could draw the forces on a separate diagram, just because you can see the left side of the equation, and then in the right you can see the right side of the equation, which sometimes might get confusing if you have the same two two things that might represent the same thing in a same diagram. So it's important not to know how to identify them and to separate them in order to identify the right equation. That's what we did on the homework. So yes. And that was for cylindrical coordinates, but then there's another topic which is that's for normal and tangential, which is cylindrical coordinates. And then we have another topic. Sorry. We have cylindrical coordinates, u r d theta, right? From here. Yep. And then we could also have a different set of components of axes of components, normal and tangential components, right? So we didn't derive this equation, but we could do it from the geometry of the example. That equation describes the behavior of the radius of a curvilinear motion, right? So it's not a fixed radius. It could be changing with the change in x and with the change in y with respect to each other, right? That's pretty much what it means. And that's what we did on this question. Then finally, going to the last lecture, this time we have the transverse. Let me see. Where did it go? No. Okay. Oh, well, yeah, I forgot to mention this is called the radial component and the transverse component for polar coordinates. And finally, for lecture 20, in particle kinetics, all right, we're only analyzing particles. I forgot to mention that. This is only particles, so not rigid bodies yet. We'll do that on MAE30B. For particle kinetics, we didn't derive it neither, but we got presented with equations that describe the acceleration, the radial acceleration, and the angular acceleration of a of cylindrical coordinates. So on the homework or in the examples that we did in the same lecture, we were able to get the acceleration before even we got the forces, and then we got with the acceleration and the mass component and some other forces, we were able to solve for the unknown force, right? So we were presented with these equations that we utilize. I guess just important to know to distinguish from this type of cylindrical coordinates and the other normal and tangential components is that for the other normal and tangential components, you could have a circular case in which the radius is constant. But as we saw, I could also have a curvilinear case in which the radius is not constant and it's just changing just because the surface is changing curvilinearly, right? Can be a like the carbon in a on top of a parabola. The radius will be changing all the time. In this case, we also have a fixed radius, but we have a fixed origin of the radius. That's the main is the main difference. So for this type of case, I guess that's how I will identify to use this equation is by knowing that there's a fixed point of reference for where the radius starts. It might change as a function of the angle, but the point of origin is gonna be there. And we have the equations that describe that. So here we were given the radius of a function of theta, and we were given theta dot, so the derivative of the change on the angle, not the derivative of the change of the angle. The change of the angle, which is the derivative, right? And we were able to use kinetic information and equations to solve for, well, I'm not seeing this question, to solve for the unknowns that they were asking for. I actually don't remember seeing this part of I don't think that I see this. So let me go through this and tap this video. Block A has a mass of 10 kilograms, and blocks B and C have mass of 5 kilograms each. Knowing that the blocks are initially at rest and that B moves through 3 meters in 2 seconds, determine the magnitude of the force P. Where's force P? Oh, okay. The tension in the core AD, neglect the mass of the pull is and axial friction. So from the notes of this problem, since it was initially at rest, I guess that's 0. But yeah, so this is a kinetic problem. As we see, the professor drew the FBD for each block, and it drew the KD kinetic diagram for each block. And by considering each block, she was able to identify the forces, knowing that it's the same cable, and identify the accelerations of each with the gain information also, because she got information for the different accelerations in some cases. And then she was able to solve for the unknowns using kinetics, nothing related to curvilinear motion, just kinetics and dimensionality of the problem. So knowing how they'll change in length of the cable will be related to the velocity of the block, right? So that's what she did. But I think this will be all for it. There are 20 lectures just by myself. I guess it's a good review. I'm gonna continue to practice for the final on Tuesday just by doing the final prep guide and just doing homework problems as fast as I can. And I think after this review, that should be enough for me to get a good score on the final. That is, oh, this is what we did in class. Okay, well, didn't expect that. All right. Oh, thank you, Brian. Well, I don't know if you guys watched it, but if you did, thank you for watching. And thank you for the 3 points. Bye bye.